In this video, we're going to find the antiderivative of the square root of x squared plus 4, and we're going to use the fact that the integral of secant cubed is this, which I've done in another video. I'll put a link in the description if you want to see that. But let's see how we get to that so that we can use that. So what we have here, because of the plus, this is going to be a trig substitution, and the substitution we're going to want to use is we're going to let x be 2 tangent theta, and you're going to see why very quickly. But before we sub that in, it's always crucial to find your dx right away, because a lot of times that gets forgotten and lost in the mix. So there's our substitutions. So what that means is I am going to be putting in 2 tangent theta in here, plus 4, squared, and 2 secant squared theta d theta out here. Now the reason we had chosen tangent as the trig substance for the trig function for the substitution is because of the plus, because it's going to work out really nice with our Pythagorean identities. And under here we end up with 4 tangent squared theta plus 4, and out here we just have the 2 secant squared theta d theta. And now I can factor a 4 out of here and pull it out of the radical. So I'm going to do that in 2 steps. So I'll have 2 times the square root of tangent squared theta plus 1 from pulling the 4 out and then taking its square root, and then 2 secant squared theta d theta. Now the advantage of this is tangent squared theta plus 1 is equal to secant squared. That's one of our Pythagorean identities. It's why trig substitution can be so valuable. And the 2 times 2 is a 4. I'm just going to pull that out of my integrand. And so what I have now is the square root of secant squared theta d theta. Square root of secant squared theta is secant theta times secant squared theta gives me a secant cubed theta. So you can see why that derivation of secant cubed theta is so valuable. And again, if you want to see that done, I have it done in another video. So let's use our rule here. So secant cubed theta is 1/2. So we're going to have 4 times 1/2 times secant theta tangent theta plus ln of secant theta plus tangent theta. And we'll have a plus c here at the end. Now a lot of times, this isn't one you normally would be expected to memorize. It's a neat derivation. A lot of times we'll get this out of a table of integrals. Okay, now we do have some more work to do. The 4 times 1/2 is just going to give us a 2. But we need to get our final answer in terms of x. We started in terms of x. We want to end in terms of x. So we know that x equals 2 tangent theta. So let me show you how you can get this all in terms of x. There's different ways. I like using a right triangle method. And if x equals 2 tangent theta, then tangent theta equals x over 2. All I did was divide this equation on both sides by 2. So I call this angle theta. Tangent relates opposite over adjacent. So x over 2. And since we're going to need, we know tangent of theta, so we could actually fill that in pretty quickly. But we're going to need the hypotenuse for secant. So let's get the hypotenuse. If we call it, say, h, we know h squared equals 2 squared plus x squared from our Pythagorean theorem, or that h equals square root of 4 plus x squared. This looks really familiar. It was in our integrand. If you want square root of x squared plus 4, that would be fine as well. So there's our hypotenuse. is square root. Let's write it the same way we had it before. X squared plus 4. Now secant theta is 1 over cosine. Cosine is adjacent over hypotenuse, so secant theta is hypotenuse over adjacent. X squared plus 4 over 2. And now we need to make our substitutions. We know tangent theta is x over 2. Secant theta is square root of x squared plus 4 over 2. So 4 times a half gives us a 2 out front. Secant theta, we have square root of x squared plus 4 over 2. Tangent theta is x over 2. Plus ln of the absolute value, secant theta, we said is square root of x squared plus 4 over 2. And tangent theta is x over 2. And the absolute value and our parentheses, and we have a plus c. Now, let's see if there's any simplifying we can do here. We have a 2 here. We could multiply it by either one of these 2's so that we could cancel that out. So this first part, when we multiply it by 2, is going to simplify to x square root of x squared plus 4 over 2. When we multiply the 2 here, we'll just leave it out front, so plus 2 times the natural log of square root of x squared plus 4 plus x times a 1/2. And I'm going to show you what we can do with that 1/2. That should be an absolute value, because we can simplify this a little bit more with the property of logs. So, last step. This is already done. X square root of x squared plus 4 over 2. The only reason I'm doing this extra simplifying is you might see it if you're doing this integral with a table. So plus 2, and now we have the natural log. Because this is a product, we can split that into 2 natural logs, both multiplied by 2. Natural log of the absolute value of x squared plus 4 plus x plus the natural log of 1/2 plus c. Now we would distribute this 2 to each part, but because this is just a constant, what it is we would absorb it into this c. So what I'm going to do is I'm going to call these C1s, and for our last line we have x times square root of x squared plus 4 all over 2 plus 2 natural log of the absolute value of square root of x squared plus 4 plus x, and then plus c. And to do that, what I did is I let c equal c1 plus 2 ln of 1/2. Because that was just a constant, we can just absorb it in this constant, which we can find with some kind of initial condition.